Welcome to the Linear Algebra tape series. As you view the tapes, take careful notes. If I explain something on the tape that you do not completely understand, be sure to come by the office and get help. Don't waste a lot of time trying to figure something out if it just doesn't click. Come and let me help you. In today's tape, you should already know most of the concepts. We are going to solve systems of equations algebraically. You may have forgotten some of the material, and I may be presenting some of it in a slightly different format, but most of it should be reviewed. If it's not, you need to talk with me. Let's start by solving the 2x2 system of equations. 2/3 x1 plus 3/4 x2 is equal to 4. 1/2 x1 minus 1/3 x2 is equal to 1. Now we call this a 2x2 system because we have two equations and each equation has two variables. Or we have two equations and two variables. Now we can clear fractions by multiplying equation 1 by 12. The common denominator between 3 and 4 is 12. And by multiplying equation 2 by 6. The common denominator between 2 and 3 is 6. So we'll come up, multiply the top by 12, multiply the second by 6. And since we're multiplying both sides by the same thing, now not both equations but both sides, I'm multiplying both sides of this equation, this side and this side by 12, the left side and the right side of the bottom equation by 6. So that makes it legal. 12 times 2/3 is 8, so we get 8 x1 plus 12 times 3/4 is 9, and 12 times 4 is 48. Now multiplying the bottom by 6, 6 times 1/2 is 3. 6 times a negative 1/3 is negative 2, so that would be a negative 2x2. 6 times 1 is 6. Now we have to decide which of the two variables to eliminate. Well, I can multiply equation 2 by a negative 8/3 and add to row 1 to eliminate the x1s. So let's multiply equation 2 by a negative 8/3. So I have 8 x1 plus 9 x2 is equal to 48. Multiplying by negative 8/3, I get a negative 8 x1 plus 16/3 x2. See, I'm multiplying by negative 8. A negative 8 times a negative 2 is a positive 16. And then 3 times 1 is 3, because that's understood to be 2/1. And a negative 8/3 times 6. Well, I can reduce first 3 going to 6 2 times. 2 times negative 8 is negative 16. Now I can add the rows. 8 and a negative 8 gives 0. So 8x1 plus a negative 8x1 is 0. Now 9 is the same as 27 thirds, so 27 thirds plus 6, 43 thirds x2. And then 48 plus a negative 16 is 32. So we get 43 thirds x2 is equal to 32. Clearing fractions again, I get 43 x2 is equal to 96. x2 is equal to 96 43rds, or we get that x2 is equal to that won't reduce, so I have to leave it as 96 43rds. I could change it to an improper fraction and write it as 2 and 10 43rds, but I'll leave it in this form. Now we can substitute back to get x1. We can substitute into either of the two equations that I'll choose to use. I can use 8x1 plus 9x2 is equal to 48, or I could use the fractions, I just choose not to. Or I could use 3x1 minus 2x2 is equal to 6. I think I'll use this one. So I think I'll substitute back into 3x1 minus 2x2 is equal to 6. This gives me that 3x1 is equal to 6 plus 2x2. I get 3x1 would equal to 6 plus 2 times 96 43rds. Or I get that x1 is equal to 2 plus 2/3 of 96 43rds when I divide everything by 3. Or I get that x1 is equal to 2 plus, I can reduce, 3 going to 3 one time, 3 going to 96 32, that's going to be 64 43rds, or x1 is equal to 86 43rds plus 64 43rds, or we get x1 is 140 43rds. So our solution would be 140 43rds and 96 43rds for x1 and x2. Now one should always check their answers. To check, you must substitute back into both equations. So we had 2/3 x1 plus 3/4 x2 is equal to 4. 1/2 x1 minus 1/3 x2 is equal to 1. So we would have 2/3 times 140 43rds plus 3/4 times 96 43rds is equal to 4. We have 1/2 40 40/3 minus 1/3 times 96 40/3 is equal to 1. So we must check both of those. I'll leave it to you to verify on your calculator that this left expression evaluates to 4, this expression evaluates to 1, and that would serve as the check. We solved the problem by Gaussian elimination. Now I'm going to give you the operations that lead to equivalent systems. Using these operations to solve a system is called solving it by using Gaussian elimination. But the things that you can do in trying to eliminate the variables. The first, you can interchange any two equations. So rather than having equation 1 first and then equation 2, I could have written equation 2 on top and then equation 1 second. You can multiply an equation by a non-zero constant. Now we did that. We multiplied the first equation by 12 and the second by 6 just to clear the fraction. You can add a multiple of an equation to another equation. We did that. We added the second row multiplied by a -8/3 to the first row, or we added the second equation multiplied by -8/3 to the first equation. So those are your three operations that lead to equivalent systems. These are the three things that you can do in solving systems of equations. Interchange two equations, multiply an equation by non-zero constant, and add a multiple of an equation to another equation. Let's solve. X plus y plus z is equal to 2. The opposite of x plus 3y plus 2z is equal to 8. 4x plus y is equal to 4. First of all, notice that the third equation is already missing a z. If we eliminate z from the first two equations, I will have two equations with two unknowns. So step 1 would be to create a 2 by 2 system. Now what I'm going to do is I'm going to multiply the top by -2 and add it to the second one. So if I multiply the top one by -2, I get a -2x minus 2y minus 2z is equal to a -4. Now add it to the second equation. To get a -3x plus y is equal to 4. Now I can combine the third equation, 4x plus y is equal to 4, with the second equation, a -3x plus y is equal to 4, to create a 2 by 2 system. Now I need to eliminate the y's. What I can do here is multiply the second one by a -1 and add it to the first. So I have 4x plus y is equal to 4. I left it unchanged. Multiply by -1. -1 times -3 is +3. -1 times y is opposite of y. -1 times 4 is -4. I get 7x is equal to 0. Now if 7x is equal to 0, then obviously x is 0. If x is 0, I can go back to either of these two equations and find out what y is. Because if x is 0, this would be 4 times 0 plus y is equal to 4. So I get 0 plus y is equal to 4, or I have y is 4. That's back substituting. Now if I know that x is 0 and y is 4, I can go back to one of my original equations and find out what z is. So we know x is 0, y is 4, which gives me then that z is -2. So I have an ordered triple in the answer. X is 0, y is 4, z is -2. Now to check, you have to check into all three equations. Well, 0 plus 4 minus 2 does equal to 2. This would be 0. 3 times 4 is 12. Minus 2 times -2 is -4. 12 minus 4 is 8. That one checks. 4 times 0 is 0. Plus 4 is 4. So all three of them check. So we know that this is the solution. Both of the above systems are consistent and independent. In other words, we had a unique solution. We had one solution. We had only one solution. So, a system of equations can have exactly one solution. If the system has exactly one solution, we say that it's consistent and independent. A system of equations can have an infinite number of solutions. If it has an infinite number of solutions, we classify it as consistent and dependent. Consistent meaning it can be solved. Dependent means that one of the equations is somehow related to the other. We can have a system of equations that has no solution. If we have no solution, we say it's inconsistent. Inconsistent meaning not possible to solve, and independent. Let's look at another system. Let's solve 2x plus y minus 3z is equal to 4. 4x plus 2z is equal to 10. A negative 2x plus 3y minus 13z is equal to a negative 8. Equation 2 does not have a y. So if I can eliminate y from 1 and 3, I could use that result to end up with a 2 by 2 system. What I can do, I can multiply row 1 by negative 3 and then add to equation 3. So if I multiply by negative 3, I get a negative 6x minus 3y plus 9z is equal to a negative 12. Then combine it with the third row, we have a negative 2x plus 3y minus 13z is equal to a negative 8. Adding, I get a negative 8x, the y's will cancel, minus 4z is equal to a negative 20. I can multiply this by a negative 1/4 to get two x plus z is equal to 5. Now I can combine this row with the second one. 4x plus 2z is equal to 10. Multiply by negative 2. I get a negative 4x minus 2z is equal to a negative 10. 4x plus 2z is equal to 10. So I add and I get 0 is equal to 0. So notice what happened. Both variables cancel. Both variables cancel. Okay, we'll come back to that in just a moment, but I want to tell you what's happening. When both variables cancel, one has either case 2 or case 3 as presented above. Now remember case 2 and case 3. Case 2 was an infinite number of solutions. Case 3 was no solution. So when both variables cancel, one either has an infinite number of solutions or one has no solutions. If one is left with a true condition, one has case 2, an infinite number of solutions. If one is left with a false condition, one has case 3, no solution. So if you're left with a true condition, you have case 2, an infinite number of solutions. If you're left with a false condition, you have case 3, no solution. Looking back, we have a true condition. 0 equals 0 is true. So therefore, we have case 2, which would be an infinite number of solutions. For case 2 systems, one should write the solutions parametrically. To write them parametrically, let's go back and notice what we have. we have solved the two equations, and we've come up, or the system, create 2 by 2, and we have 2x plus z is equal to 5. In fact, we had this twice. If we looked at the other one, we had 4x plus 2z is equal to 10. Here's where the dependency comes in, because if I simply divide by 2, I would have the equation on the left. But if 2x plus z is equal to 5, then that means that z is equal to 5 minus 2x. If we let x is equal to a parameter t, that means z is equal to 5 minus 2t. So we know that x is t, z is 5 minus 2t. Going back to the first equation, we have 2x plus y minus 3z is equal to 4. Or I have y is equal to 4 minus 2x plus 3z. Subtract 2x from both sides, add 3z to both sides. Or I'll have that y is equal to 4 minus x is t, so that's going to be 2t plus 3 times z, which is 5 minus 2t. So I have y is equal to 4 minus 2t plus 15 minus 6t, or I have y is 19 minus 8t. So then we can write the solutions parametrically as x is t, y is 19 minus 8t, and z is 5 minus 2t. So the solution will be the set of all ordered pairs, t, 19 minus 8t, 5 minus 2t, such that t is a real number. Now I can write it in braces like this. T is an element of a real number, so there is your solution set expressed parametrically. When you write answers parametrically, you may not always get what's in the back of the book or even what I write on the tape. Solving equations parametrically involves letting one of the variables arbitrarily be a constant t. In this case, I let x be t. If you let y be t, your solutions would look different than mine. If you let z be t, yours would still look different from either of the first two. Now, if you substitute into the original equations, you will always get a true condition. That's the only way of knowing that your parametric representation is correct. One can use the symbolic algebra program derive to solve systems of equations. When they get ugly, you may want to go to derive. Solve 123 and 5/10 x plus 61 and 3/10 y minus 32 and 4/10 z is equal to 34 and 3/10. 54 and 7/10 x minus 45 and 6/10 y plus 98 and 2/10 z is equal to 45 and 8/10. 42 and 4/10 x minus 89 and 3/10 y plus 12 and 9/10 z is equal to 35 and 8/10. To solve using derive, of course, you go to derive and get to the main screen. Once you get to the main screen, you click Author, and then after Author, you click Expression, and when you get your expression box, you type solve, parentheses, then you put brackets and you put these equations in there. So I'm just going to put equation 1 and comma, equation 2 and comma, equation 3 in brackets. Then you put comma, you put brackets, and you put your variables, x, y, and z, and close the parentheses. Then you go and do simplify. And once you go simplify, then you get basic simplification. So if you'll follow those steps, derive will solve it for you. I have a printout from having done it with derive. I go into derive and type the author and expression, and then I type solve, and I type in the first equation, comma, the second equation, comma, the third equation, in my bracket, comma, then I give my variables, x, y, and z, inside the brackets, and close with parentheses. Just like I showed you using equation 1, equation 2. So this is how you author it. Again, the word solve, parentheses, inside the braces, you put equation 1, comma, equation 2, comma, equation 3, comma, and then your variables, x, y, and z. And notice there is a comma here between your equation brackets and your variable brackets. Now I tell derive to do a basic simplification. And derive will give you what x is equal to, what y is equal to 2, and what z is equal to. Now those fractions are extremely hard to interpret. So what I told derive to do was to approximate to 2 decimal places. So I told derive to approximate to 2 decimal places, and it gave me x is 40/100, y is a negative 18/100, and z is 15/100. And of course, on your calculator, you can just divide the numerator by the denominator, and you should get this answer rounded to hundreds. But derive does it quickly and easily. Just hit the simplify button again, and this time go down to approximate.